This is a picture of us, three aspiring mathematicians, Kenneth, Noah, and Daniel, each standing at about 7 meters tall. Or wait, 7 meters? Do we mean to put that in the script?
Well, I didn't know your height, so I just used the tree beside you as a reference. The tree has a height of 14 meters, and we're about half of a tree. I don't see the issue.
But the tree is way back there, and we're way up here, and whatever is way back there looks smaller than it really is, as if it were way up here.
But how does that make any sense?
Because it does. Here, I can show you. Imagine that this is you looking at a screen that displays exactly what is behind it in 2 dimensions. If you put an object at a distance behind the screen and increase this distance, it will appear smaller and smaller in 2D until it shrinks towards the horizon line. If you walk towards the screen, because the whole screen will appear larger, so will the object on it.
Okay, I think I'm getting it. But I still don't know how this all works. Why does an object look smaller as it moves further away, even if it doesn't actually shrink?
I've got an idea. How about we take this problem into the real world? This cube is suspended in front of a white background. Nothing is special here. That is until you turn off the lights. In order to create the scene and observer scenario like before, by using shadows, we must use the flashlight as the observer and place the object in front of the image. The light radiated by the flashlight will be blocked on its path to the image when it comes in contact with the cube. Given that the light travels with many angles of incidence out of the flashlight, the rays that barely miss the cube will continue to spread, increasing the volume of the gap created by the rays that reflect off the cube itself. The farther from the background that the gap is created, the more time that the gap has to expand, creating an image with the illusion of perspective. Parts of the cube nearest to the light source are larger than those further away.
I get it. The size of an object in an image correlates with the distance that light can hypothetically travel between the real object and the image, with the observer acting like the flashlight, just in the opposite direction. The light rays heading towards the observer that reach the edges of the object will continue in their path towards the observer, shrinking the volume of light reflected off of the object as all the rays converge into a single point, therefore shrinking the object's appearance to the observer. The size of the object in the image is, as a result, determined by the placement of the image between the observer and the real object.
That's right! We can portray this geometrically by drawing an isosceles triangle, where one point is placed at the observation point, where the light rays converge, and the others are at the top and bottom of the object. We can state that the height of the object is L, and that the object's image is placed somewhere within the shape, parallel to the object. Let's draw it here, for example. We can define the distance between the observer and the image as A, and the distance between the image and object as B, with the apparent height of the object and the image as H. Using the linear movement of light towards the observer, we can state that the percentage of the total distance between the observer and the object that is in front of the object's image is the same percentage of the height of the object that is replicated in its image.
That must mean that we can sum A and B and divide A by this total to get the percentage that we need. Then we multiply that decimal value by the object's real size to get its replicated size in the image, as culminated in this formula.
We can explain this relationship algebraically, as the triangle created between the observer and the image plane is similar, as in having the same angles, with the larger triangle made using the real object. This means that these triangles' height to base ratios are the same, as is represented here. We can arrange this to solve for h, resulting in a diminution of size formula that we discussed prior.
This incredibly useful technique is used almost universally in all forms of imagery and art. M.C. Escher used the diminution of size to blend objects far and near, creating confusing, seemingly depthless art pieces. Judy Chicago's 1974 work, The Dinner Party, revolutionized this style by installing many objects of the same size, in this case dinner tables, in an evidently mathematical pattern that showcases both the diminution of size and, through this phenomenon, the immensity of social stigmas against the forthcoming of women's struggles in Western culture, through the seemingly endless triangle of tables, each representing an unspoken story.
Who knew that the geometry of perspective could shine a light on such an important social commentary? On that note, we should probably get back to reading our script.
That's right. Where were we? This is a picture of us, three aspiring mathematicians. Last week, we went down to Daniel's 1,072-story house. What? 1,072 stories? How did you even get that number?
Well, I just compared the size of the house to the clouds in the background.